Hello students, today we are meeting with a lecture which is lecture number 19, where we are planning to discuss the condition where the electrostatics and magnetostatics, how the discussion on the electrostatics and magnetostatics can be taken to the case of dynamics. So which means that in all the previous lectures we have been discussing the case where the charge density is independent of time. And the same is the case of the magnetostatics, where we say that the current density is independent of time. So, how the current density will be independent of time is that when the charge density does not change with time, charge can move, that is not a problem. Only when the charge is moving, you will get the current. So, when the charge moves, we don't say that the charge density is the function of time. So, there the word density is what you have to pay the attention. Charge density means number of charges per unit length. So that will not change when the charges are moving. So that is what we mean to say the magnetostatics. So charge density should not fluctuate with time. So if that is the case, we say that the current density is uniform, and in which case the magnetic field generated is also uniform. Uniform means constant. So similar situation. So all these conditions we have done already, which means that we know how to write down the experimental observations into the corresponding vector form, and how to exploit the vector calculus, that means some of the product rules and some of the properties of the vector functions and theorems we have been using to establish certain equations what are known as the Maxwell's equations. So by now writing down all the equations together in one place, we will be able to understand the whole concept together in a single place. Okay, now that we have seen different equations scattered in different lectures, so if you can write down all the equations in one place, your understanding will be better. So once we do that, that is also going to be helpful for you to make a transition from the static case to the dynamic case, wherein we consider the charge density that can fluctuate with respect to time, so that we will be having time dependent electric field and time dependent magnetic field. So we can then naturally ask the question, what is the in what is the methodology that we can make a transition from statics to the dynamics. So when you are making a transition, we don't use the word two different words here. So one is the electrodynamics and second one is magnetodynamics. So we don't require two terms for that. Electrodynamics naturally involves magnetism naturally. Okay. So you don't require an additional terminology called magnetostatics. Sorry, magnetodynamics. So that is the reason why we have a common name. Only electrodynamics is sufficient. Or instead of electrodynamics, you can say electromagnetic theory. So we are going to see later that the phenomenon of electricity, or we say the phenomenon of electric field and the magnetic field, they are indistinguishable from a relativistic point of view. So that will be understood later when we discuss the relativity. So because of this reason, what happens is you don't require two names. Magnetodynamics is not required. So that is the reason only one name is enough, electrodynamics. So what we will do is that whatever equation that we had in the last several of these classes, let us write down in a proper way so that the entire thing becomes simple in one place. So I will now show what are the Maxwell's equations that we have derived till now. So here it is there. So what are the equations that we have till the last class? Are these four equations we have actually derived? I mean, we have proved how these things can be established. And there is a point to be noted that some of the equations have the condition that it is valid only for the electrostatics and magnetostatics, whereas the equation with the divergence, they don't have such kind of restriction, which means that equation number 1 and equation number 3, they are valid even for the dynamic cases, because while doing the derivation we did not make any assumption, or we did not consider some special case. Therefore, the divergence of electric field given by the charge density by epsilon naught and the divergence of magnetic field 0, they are valid all the time. That means whether we are discussing the static or the dynamic case. But however, as you can see, because of the suffix 0 here for epsilon naught and mu naught here, these equations are generally or these equations are valid for vacuum or air. Okay, other than vacuum and air, this equation has to be modified in order to accommodate the dielectrics, and here you have to accommodate the magnetic material. So other than that, these equations, you need to know the validity, namely that this is the set of equations for vacuum and this is the set of equations for static condition. So the moment this is clear for you, it is therefore natural to rewrite this expression in the integral form. So once you write all the equation together, you will be able to understand. So let me therefore write down how to rewrite these equations. How to means not the explanation. We already know them. We are going to simply make the summary of what is available to you. So the first equation can be written down as the E dot ds. Okay, that is the Gauss law, which is equal to the Q enclosed divided by epsilon naught. So the same equation, what is written down, the first equation has been, we have already seen how this can be written using the Gauss divergence theorem. Now the purpose of writing this equation is that you have to list out all the equations together so that you will be able to give the connection between the divergence and the surface integral. You always see this. Whenever the divergence is there, you'll be having a surface integral, and whenever the curl is there, the integral will be a line integral. So that is a point that you'll have to notice, so that when we write all of these equations together, we will be able to give some kind of connection between the equations, and that will help you to understand and therefore remember better. Okay, so let us therefore write down the second equation, maybe the divergence of B. So we can write down that the B dot ds will be equal to 0. Equation number 3. So I'm not going to change the equation number, so that is same equation rewritten in integral form. And now you'll have to write down the dl. So L means it's a line integral. So the difference is that this is a line integral, the previous one is a surface integral. And once again you can write down for the Ampere's law, and therefore we can write down I enclosed. So the reason why we say enclosed is because it is inside a certain loop. Okay, that is the reason, and this is of course quite trivial in this particular case. Q enclosed is because this, if you want to evaluate this integral mathematically, you need a surface. So this closed integral is a surface. So you have to draw a mathematical surface. So inside that mathematical surface, what charge is residing inside? How much of the charge is residing inside that surface? That is what we mean to say enclosed is here. So any charge that is going to stay outside this mathematical surface will not be counted for doing the calculation. So similarly, this is also the same situation. You are going to draw a loop. Okay, this is not a surface. This is a loop, which is a one-dimensional curve. Okay, so the curve will occupy two-dimensional, but however it is a path. Okay, so it's not a straight line path, it may be a curved path, and then it is closed path. So inside that closed path, how much amount of the current is flowing? So there may be some wires that may be lying outside the loop. Okay, such wires will not be counted for the calculation. That is the reason why we use the word enclosed here. And of course this particular equation clearly tells that you don't have, or we say that absence of the magnetic monopole. And when you compare these two equations, that means 3 and 1, both the equations are looking similar on the left hand side. On the right hand side you have 0, here you have Q. So Q is a single charge, right? It can be plus Q, I mean collection of single charge, whatever it is. So it is a kind of a plus Q or minus Q. You can also have single charge allowed. So which means that since you have the single charges there, which you may have a plus Q or a minus Q, so it's all fine. And therefore what happens is that the single charge enters into picture in our calculation. Now 0 indicates that single charges are absent. That means single charges means corresponding to the magnetism. So we say that a north pole, or we say that the north equivalent charge, The equivalent to the charge is what we say pole. Okay, so what is known as a charge in electrostatics is that is the one known as pole in the case of magnetostatics. So therefore we say that north pole or the south pole uh, doesn't appear as a single element, and therefore 0 is present here. If they were together, then that combination is not there in this equation, and therefore it cannot be reflected here. If you see the case of the dipole, it will be reflected in both the places. Electric dipoles are present and magnetic dipoles are present. Magnetic dipole means a combination of north and south. That is of course there, and that is why you can always perform magnetic monopole expansion. Not possible. Magnetic dipole expansion possible. So the point to be noted is that when you perform the multipole expansion, we have done of course the multipole expansion for the electric field, and similarly if you perform the multipole expansion for the magnetic field, you will discover that the monopole term will go to 0. So the minimum non-zero value will be corresponding to the dipole only. So these are the evidences that you will be having to demonstrate that the magnetic monopoles do not exist. So this is the meaning of the equation number 3. So corresponding to this, maybe some of the names are, I will just write down for comparison. So equation 1 is known as the Gauss Law. Equation 2 has no names. Equation 3 also there is no name for equation number 3. And equation number 4 is known as the Ampere's Law. So these are the things, and some of the textbooks will give some equivalent name like Gauss Law in magnetism, but that is not correct. So that is why I am specifically writing here. And the collection is what is known as the Maxwell's equation. So when you are writing the word Maxwell equation, you don't have to worry about giving number 1, 2, 3. So you can give anything as equation number 1, anything as equation number 4. It's just arbitrarily we can give. But what is known is that the collection of the 4 equation is what we call the Maxwell's equation. And when we move on to the case of the time dependent situation, one of these equation will gain the name. Okay, but right now you don't have the name for these two things. Ultimately equation 2 will not have any name. Equation number 3, this particular equation will not have any name. We are going to modify the static situation, and therefore equation number 2 will get a particular name will come for here. So these are the points to be noted. And I would like to further write down that the another collection of equations where we write down some of the additional expressions are required. See, only these Maxwell equations are not sufficient. Some extra information is required. So I will write down, in addition, we have the following additional information. You already know that. So that is why I am writing them together here. So what extra information is required is that the electric displacement vector for the case of the dielectric medium, so D vector is equal to epsilon into E. So that epsilon can be written as epsilon 0 epsilon r. And similarly for the case of the magnetic material, you can write down mu naught mu r into H vector. And in addition to that, very important equation is there, and that is the Lorentz force equation. So Q into E plus V cross B. So these are the additional information which are very much required in addition to the Maxwell equation. So that's why I'm writing down. And there is another equation which you have been discussing, what is known as the continuity equation. So that you know that dou rho by dou t equal to 0. So, but however, this equation will not be counted. So I will explain why it is so. So how we are going to call this equation is that equation number 5 and the 6. Okay, equation number 5 and the 6, they are known as the constitutive relations. Whereas the equation number 7 is known as the Lorentz force law or Lorentz force equation, and the last one is known as the continuity equation. So there is a point to be noted about the continuity equation, that this particular equation, namely this number 8, right, equation number 8, is not considered or it is not an independent equation. It is not an independent equation. So I will explain what is the meaning of this. But however, the point to be noted is that the constitutive relations and Lorentz force law, they are required over and above the Maxwell equation. That is very important. So therefore, let me therefore write down what is the conclusion. The conclusion is that if you want to study the electrodynamics properties, or we say electromagnetism, for the static situation, then equation number 1 to 4, that is Maxwell equation, together with 5, 6 and 7. These are the equations required to, or we say that these equations explain the complete electrostatics and magnetostatics. So why I am making this particular statement is that you may try to neglect equation number 5, 6 and 7. So if you delete to 5, 6 and 7, then 1 and 1 to 4, that alone cannot explain. That is what I am trying to say. Okay, 1 to 4 cannot alone explain. So in addition to 1 to 4, equation 5, 6, 7 are required in one or the other place. Somewhere it is required. Okay, so therefore if you they are required in order to make the completeness. Completeness means, certain phenomena cannot be explained without 5, 6 and 7. So that is the point we noted. And coming to the 8 is not independent equation, in the sense that what is the meaning of saying that it is not independent equation is that it is possible to derive the equation number 8. It is possible to derive this particular equation from any of the Maxwell equation, maybe any one of them, not all of them. Somehow you can consider the 4 equations and then establish equation number 8. So because of that reason, this particular equation number 8 cannot stand independently. So that is the meaning that I am trying to say, and therefore let me write down this statement, same statement. Is not included in the list because the reason is because it can be derived from the collection of Maxwell's equations. So whatever we have written till now is, of course, they are all valid for vacuum. So a small change if you do to this set of Maxwell's equation, we will be getting the corresponding equations for material medium. That means dielectric medium or magnetic material. So therefore, this is important, very important point, that in the case of the linear, homogeneous, isotropic material, so this combination should go. Linear means, linear means also homogeneous and isotropic, they go together. So any material media that we are going to consider is linear, homogeneous and isotropic. So you need to know their appearance of the Maxwell equation. So therefore let me write down that the divergence of the D vector will be equal to the rho free. You have to write down them, otherwise only when you collect them in a one place, that how many equations are there, how many are independent, so this knowledge will come. So that is the reason why I am writing all these things. And corresponding to the divergence of B, we can have like this, divergence of H equal to 0. Coming to the curl, we have curl of the D vector is equal to 0, of course statics. Okay, and finally we have the curl of the H vector is the current density J. So we can give some numbers here, whatever be the number, not a problem. So before writing the integral equations or the integral version of the equation, what do you understand? Let me first of all tell you here that you need to be careful about the word free here. That is the reason why we are writing it once again. You cannot think that all these 4 equation you can generate easily from the vacuum equation. So that is why I'm trying to capture some of the point. The word free will not come if you simply copy the equation corresponding to the vacuum. Okay, that is first point. Second point is that when you are writing the equation in the material medium, the quantities such as epsilon 0, epsilon r, and in this case mu 0 and mu r, all these things will be absorbed. So that is why it will not be visible explicitly. They will be absorbed inside the H vector, and they will be absorbed inside the D vector. So the D vector will have all information about the epsilon r, that is the what you call the dielectric constant of the medium. Of course epsilon naught is it is there inside in order to make the dimensions agreeable. And similarly here you have the relative permeability and the mu 0, both of them are there. They are contained inside the H vector. So therefore when you are writing the expression in the material medium, those constants will not be appearing in the equation. So that is the reason. Otherwise, mu 0 into that this is mu naught into j. So that mu naught will be absorbed inside the b vector and got converted to the h vector. So that is the reason why I told that we will have to be careful with the constitutive relations. So those constitutive relations are, once again, remember, they are valid only for the case of the linear, homogeneous, isotropic material. So these things are very important because for the case of the nonlinear, inhomogeneous, anisotropic expression, we will have to perform numerical calculation. They are not simple, and therefore you cannot easily treat them by an analytical method. So that is the point. And then once again, equation number 2 and equation number 4, they are valid only for the static situation. So the set of equations that is written down here is once again valid for the static condition only. So at the end of the, after finishing all these things, we will discuss how to move to the dynamic case. But before that, let me write down equivalent integral form of the equation. And divergence means you will be having a surface integral. So once again, you have to write free here. Okay. And whenever you are having the curl, you will have to put the line integral. That's why dl will come. So that is a common feature of the divergence and curl. So once again, we have the divergence, right? So put the surface integral. Then you have the curl, therefore you put the line integral. So this is the current, which is, of course, it is current enclosed in the circuit. So you can write the suffix I enclosed if you want. So once this is clear, that you will be now knowing how to write down all the equation. And now what I am trying to say is that we have electrostatics and we have magnetostatics. So what are the common features? You can compare it and then see the entire phenomena in a single place. So in the case of the electrostatics, you have a source, which is the charge density. In the case of the magnetostatics, the source is the current density. So because of the charge density, electric field is generated. Because of the current density, magnetic field is generated. Electric field can also be understood in terms of another quantity known as the potential. So remember that the charge is not generating voltage, charge is generating E. So remember one thing, that the charge density, whatever is there, right, the charges, they will not generate potential and electric field. It is not going to create two of the physical quantities. The charge density or charges are there, right? That will not generate two physical quantities, one called potential, another called field. It is going to generate only one. What you are going to call and how you are going to interpret, that is up to you. So the point is that there may be a force. You can always say electrostatic force surrounding them. In that case, you have to write down F here. So whether you are going to consider the force or whether the surrounding region is filled with a field or the surrounding region is filled with a potential. So these are the concepts, equivalent concepts, that you are going to have. So the point is that surrounding the charge density, you have only one, whatever be the name that you are going to give. The other name, for example, if you are going to say the other name is the potential, that is an equivalent representation for the electric field. That's all about it. So this is equivalent representation. We can always convert from one to the other. So there is a source and there is a effect. So we can say that the source is the charge density, the effect is the electric field. And our equivalent understanding will be in terms of another quantity known as the potential. And the story is once again same here. We have the current density, which is the source, and the effect will be the magnetic field. And the same magnetic field we can understand in terms of another quantity known as the potential. So this is the reason why the name potential is coming, because we already know that this quantity V is known as the electric potential, and we would like to call by a similar name because all these things are looking very similar, and therefore we can call this particular object as the magnetic potential. But there is a big difference, that this is a vector quantity, this is a scalar quantity. Therefore this particular potential is known as the electrostatic scalar potential, and this particular quantity is known as the magnetostatic vector potential. So vector is there here. So that is the reason why it is known as the magnetic vector potential. So that's fine. So now you know that this is how you have the sources and then the field is there. And the point is that we have equations relating all of them. We have done it, of course, over the last all the whatever courses that we have done, uh, including you consider including whatever you learned from BSc also. So all the time you are studying the electromagnetism, we have the equations that relates charge density, electric field, potential. And similarly, in the case of the magnetism, the current density, magnetic field, and the magnetic vector potential, we have the equation. So interestingly, in the Griffith's book, you can find out a diagram in the form of a triangle that gives you all the relations in one place. So this is the interesting point. Learning everything in one place will give you a better understanding and also easy to remember. So I will show that particular diagram taken from the Griffith's book. So this is the expression. Let us see how many of them are there. So we have the charge density. So from the charge density, the effect of the charge density will be either you can understand in terms of the electric field, or equivalently you can understand in terms of an electric potential. Now whatever be the case, you have the mathematical equations connecting one to the other. So how to read this particular equation is this arrow you'll have to see. Now what is the meaning of this particular arrow is that, so this is from the tip of the arrow represents 2. So from means given to you. So if the charge is given to you, then how to find the potential? That is a question. Answer is this: potential equal to. So when you say potential equal to means how to find potential means this is the answer, not this one. There are two equations are written, right? So you have to be careful which one corresponds to which one. So now it is clear that whichever is the arrow is pointing, and that is the quantity to be calculated. So therefore the quantity to be calculated should be written here, and then equal to is there. And therefore this is the quantity that you are evaluating, and in the evaluation you have the charge density. So because it is given to you, you know it, and therefore we can put here and then evaluate the integral. And similarly you can understand the rest of the equations. But there is a point to be noted: if you are coming to this particular situation, you see here this situation here, consider this arrow that is going like this, and then this is the tip of the arrow. So that means, given the electric field to you, electric field is given to you, find out the charge density. That is a question. But you see how many equations are there. This is not a single equation. Okay, this is the point to be noted. You have two equations. This means, so what is the meaning? The meaning is a single equation is not available to you to calculate the charge density if electric field is given to you. That's the meaning. So how many equations are required? You need two equations. And in particular, what are those two equations is, one is the divergence of the electric field, the second one is the curl of the electric field. And this is very important consequence of a very famous theorem in vector calculus, what is known as the Helmholtz theorem. So Helmholtz theorem says, the statement is quite simple. Of course I will tell you, the statement is very simple. That is, I have some vector quantity. Okay, that some vector quantity you consider as E. Okay, in terms of mathematics, E doesn't mean electric field, it can be any vector field. That's all about it. So mathematics says, what mathematics says is that if you can provide the divergence of the vector field together with the curl of the vector field, if you can provide that, then I can calculate what is the field itself. Is the point is clear? See, the question is, what is the question is, I don't have the value for E. E means some E field, okay, whatever it is, whether you call it by electric field or whatever name it is. E is a mathematical field that you have according to vector calculus. What I don't know is, I don't know the value of the E vector itself, but instead of that, I know its divergence and I know its curl. So Helmholtz theorem says that if you know the divergence and if you know the curl together, then it is possible to determine that particular vector uniquely. Uniquely is very important. Okay, if it is not unique means you can find many different answers for that particular vector. Then it gives you a lot of chaos there. So uniqueness is very important. This is what is also known as the uniqueness theorem. Uniqueness means, provided that you know the divergence and the curl of a particular vector together. So together is very important. Both of them should be available to you. How it is available is, divergence is given by rho by epsilon naught, curl is given by 0. So both values are known to me. So a combination of divergence and curl will enable one to evaluate the vector itself uniquely. So this is the reason based on the Helmholtz theorem. So the answer is this. So therefore, you should also remember that if a question comes like given the electric field, how to determine the charge density, like that, if a question comes, then you should be able to explain in these lines. And similarly, you can always understand from the arrow and the corresponding equation, and all these equations we have derived and they were there in our previous lectures. So now the advantage is that in a single place you are simply listing out all the equations together. You're not missing out any equation. Everything is there here. So that is why this particular the Maxwell equation is what we say all everything under the electrodynamics comes under one roof. Okay, and that is the set of Maxwell's equation. But there is a together. So what is the together is that the constitutive relation is required, and then the Lorentz force law is required. So this is something required over and above the Maxwell equation, so that everything of the electrodynamics can be discussed. So that is the point. And the let us now see what will happen to the three quantities for the magnetostatics. You have a similar triangle structure, and you can write down all the equations. I'll show that now. So this is the diagram showing very similar to the case of electrostatics, and all the equations are quite familiar to you. We have been seeing, except for one or two. Let me therefore explain what is that one. And but other than that, you can always understand how to calculate it. In particular, let us see this one. In particular, I think the last lecture or the previous two, I mean 17 or whatever, the last two lectures, if you see, this equation will be there, so that you may be remembering this. So we are going to call the A vector as the magnetic vector potential, and we have seen this exactly. And remember that the script r is nothing but modulus of r minus r prime. So all the equations in this are quite familiar. Once again, there is a similar situation is there. We have the curl of the vector, and then the divergence of the vector are specified. Specified means given. It is specified that divergence of b equal to 0. It is specified that curl of b is mu naught j. If it is the case, if it is specified, the question is calculate the j. Isn't it? So the point is clear, right? So here b vector is the b vector has to be is already provided to you. So the question is that how will you calculate the j vector? And therefore, in the similar way, when you want to perform calculation, divergence and the curl will go together, because only when the divergence and the curl is given together, only then the vector itself can be calculated. Vector itself means whichever vector is common to them. So A is common, right? Therefore, A is the quantity that you can calculate. That is the meaning. So whichever is common here, that quantity is going to be calculated. So here E is common here, right? Therefore, E can be calculated. So this is the direct consequence of the Helmholtz theorem in the vector calculus. But in this, there is a point to be noted. In the list of the equation, I think there are one equation is there here. This equation you might not have seen. So therefore, there are two equations. Yeah, I will tell you this equation. So del square A equal to minus mu naught j, and then the divergence of A equal to 0. These two equations we have not obtained till now. All other things we have obtained. So therefore, probably I'll write down so that it will be clear that out of all this discussion, two of these equations are not derived by us, or I have not explained to you. So therefore, I will write down the two equations are the divergence of the magnetic vector potential, and then the Laplacian of the magnetic vector potential. We have not explained anything. And this is interesting topic, most important topic, and I will write down that these equations are related to what are known as gauge transformations. So this is the point that you keep it, and when I am explaining the gauge transformation, we will be reverting back to these two equations. So this is the point to be noted, and this gives you now a complete overview of the set of all equations that we have studied in the previous classes. And therefore, probably I will before entering into the transition from the static to the dynamic case, I want to explain why the continuity equation has to be removed from the list. I said that what is the list of equation required to understand electrodynamics? The answer is Maxwell equation plus constitutive relation plus the Lorentz force law. That's all. Continuity equation is not there in the list. The question is why you are removing it. So the answer is that it is not an independent equation. So I will take 1 minute to explain why it is not an independent equation. So I think this board is full now. So I'll go to a different place and write down. Yes. So here, this question, whatever I told is already written. Divergence of the J, the same continuity equation is written. What I am trying to explain is that since we are discussing the static situation all the time, the dou rho by dou t is supposed to be 0. So therefore, continuity equation, first of all, you will have to understand that the continuity equation is given by divergence of J equal to 0, because this term will not be there. Till now statics, right? And only from tomorrow or whatever you call at the end of the today's class, we are going to make a transition to the dynamics case. So for all the static cases, we have the dou rho by dou t equal to 0, and therefore the continuity equation is given by divergence of J is equal to 0. Remember that. So the question is, can we derive divergence of J equal to 0 using the Maxwell equation? That is the question, and we are going to say yes. So how we are going to say? Let us consider one of the Maxwell equation that we have been discussing in the last two classes, namely the Ampere's law, and take the divergence of that equation. So divergence of the curl of the magnetic field is equal to, once again, divergence of the mu naught into J. And your vector calculus says that this is 0, and this will give you divergence of J. Now this is very important. Divergence of curl of any vector is 0, not for magnetic field. Okay, mathematically speaking, B can be any vector. For every such vector, divergence of curl is 0 always. That is the reason why there is a 0 here. And here, of course, you get the mu naught is a constant. So that mu naught is a constant coming out, and because this is 0, I am cancelling. So ultimately, only divergence of J I am going to write down. So therefore, ultimately, what did you get? Ultimately, we are getting divergence of J equal to 0. That is what is the continuity equation. So our conclusion is continuity equation is buried inside the Maxwell equation, or we say that the continuity equation is hidden. It is hidden inside the one of the Maxwell's equation. That is the conclusion. And in particular, one of the means which one? One of the means here this expression is the Ampere law. So in particular, you can say that the continuity equation is hidden inside the Ampere's law. So that is the conclusion. So let me write down whatever I explained now. So this expression is equal to whatever it is. How you got 0 is, dou rho by dou t will be equal to 0 for the static situation. So that is the reason why we are considering like that. Okay, so this is first point. And there is a second point that I would like to write down. I will like So all these things we have explained for the static case. So in case if you want to move to the dynamic case, then there is a point to be noted. So that point I will write down that the meaning is that if rho is a function of time, I will write down if rho is a function of time, then it should be reflected in the Ampere's law, isn't it? So are you able to understand this? It should be reflected in the Ampere's law. So this should be clear to you. Only then you'll be able to appreciate for the further work. Now what I'm trying to say is, you are asking the question, where is the continuity equation? The answer is, continuity equation is hidden inside the Ampere law. It is not visible to you, but it is hidden. Now how are you going to bring it outside is by taking its divergence. So that hidden quantity will come outside if you take the divergence of the Ampere's law. Then you are asking further question. What is the further question is, suppose if the charge density is a function of time, then dou rho by dou t is not equal to 0. So this quantity is not going to be 0. Then in which of the Maxwell equation this information should be hidden? That is the question. In which of the Maxwell equation this information will be hidden? This information means dou rho by dou t. Where it will be hidden means it will be hidden only inside the Ampere law. So that's what I am writing, that in case if the charge density is a function of time, that means if you want to discuss the dynamics of the charges, okay, now we are interested to move from the statics to the dynamics case, then which Maxwell equation has to has to reflect that information, that what you call the time dependence. So the answer is that the Ampere law has to be modified, or the Ampere's law has to reflect the time dependence of the charge density. So that means the appearance of the Ampere's law, that is looking like this, right? This appearance has to change. It has to show. It has to show where is the time dependence. That is the meaning. So this knowledge you are now getting, because you are now in a position to understand the where the continuity equation, the information about the continuity equation is hidden, or it is buried inside. Okay, so therefore, the point to be noted is that we have to look into the derivation of the del cross B equal to mu naught into J. We have been doing the derivation for the two classes, right? So you have to be careful about that, and then you have to pay attention to that. That is what I am trying to say. Okay, so this is one thing. So once this is clear, now we are comfortable. I think now we are ready to move to a next place and then discuss the transition from statics to the dynamics case. So therefore, I would like to write down that we are interested to make a transition from the electrostatics magnetostatic case to the dynamics case. So you know where the information is present, and you also know which of the Maxwell equation has to be modified. So I will now first of all write down therefore that for the time dependence, right? Now we have to collect the information about the time dependence. So you are basically asking the question, if you want to study the time dependence properties or the phenomena, that means the time, what you call the changing electric field and the time varying magnetic field. If you want to study these things, do you have an appropriate experimental evidence? This question, why do you want to ask, is you should again remember once again that in the very beginning of the electrodynamics itself, you can't start vector calculus without anything, without any input. I mean, physics, you should have a physical input. Physical input means an experimental evidence. Only then you can proceed further for mathematical calculation. In classical mechanics, you have the physical evidence, right? The Newton's laws are there, which are experimental evidence, and based on that only we have developed the Lagrangian formulation, Hamiltonian formulation, etc. Similarly, when you are starting or discussing the electrodynamics, okay, it is not the pure vector calculus that you have, but you can work with vector calculus. But what is the input coming from the physics or input coming from the experiment? So they were the Coulomb's law and the Biot-Savart law. So with these two things only, we have been rewriting the expression in all possible ways to understand the electric and magnetic phenomena. So that is the reason why we are now asking this question. The question is that, experimentally, do you have any evidence and information about the time dependence? That is a question. The answer is, of course, yes. You already know what it is. So one is the Faraday's law. I will write down and show first of all. So where the time dependence is coming, one is the Faraday's law, you have time derivative. Continuity equation is the one where you have time derivative. So I'm talking about time derivative. So you already know the Faraday's law, the voltage generated in a circuit is equal to minus d phi by dt, where phi is the magnetic flux. So therefore you can always rewrite this now in a vector form. So therefore I will write down like this. So here the phi represent the magnetic flux. Okay, of course the flux is a generic term. You can have heat flux, you can have electric flux, magnetic flux, etc. So flux is a general terminology. So here it is magnetic flux, and B is actually magnetic flux density. which means that the amount of the flux divided by the area. So that should be clear to you. Only then you can understand how the equation comes. So I will write down that is the flux or magnetic flux, and this is the amount of the magnetic flux divided by the area that is perpendicular to it. So the knowledge about the the perpendicular, it comes from the dot product that is there. So dot product tells you the normal component. So that is the meaning, and then the d by dt is written here, so that is fine. And what is known from the previous knowledge is that the line integral, this is supposed to be a line integral. So the line integral of the electric field along a particular path, whatever be the path that you have, that will be the electric potential. And since we are going to measure the electric potential in a closed circuit, this is the experiment, right? So you are going to have a circuit which is closed, and therefore the path should also be a closed path. So I will write down that. So once you know that this is a closed path, you can write down like this, and then here the word magnetic flux density is now clear. So this is the reason most of the time B is referred, B means this B vector, B is referred to as magnetic flux density is better, is more accurate term than the magnetic field. Okay, so magnetic field we can use, when we can use the magnetic field is when we are going to consider inside the magnetic material. So this is the general terminology. Whenever you are going to discuss the magnetic flux density inside a magnetic material, then that quantity is known as magnetic field, and the corresponding symbol will be H vector. So that is the reason. But otherwise, when you are not discussing inside a magnetic material, that means whether you are discussing in vacuum or in air, whatever be the case, the name is magnetic flux density. So there is a distinction is there. Okay, but unless you are not going to worry about that particular discussion, we generally call by the name magnetic field. But this distinction is very important. Okay, the reason why it is very important is that inside the magnetic material you have the quantity mu 0 and mu r that will be playing around this, isn't it? B equal to mu h, right? And therefore what happens is B divided by mu, this is a B vector, divided by, you have to put a mu, that is the permeability. So that quantity is only called magnetic field only after dividing by mu. That means the dimensions are changing. Why we are so much worried is that the dimensions will change. Okay, for the case of the magnetic flux density, your dimensions are Tesla, or we say Weber per meter square. Okay, so Weber per meter square is not the dimension for the magnetic field, it is the dimension for the magnetic flux density. So that is the reason why this kind of important distinction in the terminology is required. But otherwise, once you understand that we are always discussing in vacuum, then people generally tend to use the word magnetic field for the capital B vector. Okay, fine. So once these things are clear, and this being the closed circuit that we have, we can write down like this. And now you can you can once again use the Stokes law, because Stokes theorem tells you the connection between the line integral. That is why, because we have a line integral, we will apply the Stokes theorem to the left hand side. So that means I am going to convert it to a surface integral. So therefore I will write down the surface integral of the curl of the vector field. So curl of the which vector field means we have electric field, that should be a normal component. Whenever you perform a surface integral, it's a normal component. That's all about left hand side. Right hand side, I'm not going to do anything. Only thing is, let me interchange the order. I'll put the integral first. I will take the differential inside. And when I am taking the differential inside, I will convert it to a partial derivative. And that's all about it. And so naturally the question will come. So the question that you can ask is, this is like a total derivative d by dt, but here it is written as a dou by dou t, partial derivative. How it is changed? Okay, that is first thing. Second thing is that here the derivative operator is first, integral operator is second, but here it is interchanged. So first we are performing derivative, and finally only we are performing the integral. So how the order can be changed? The answer is, both the answers are quite simple. As you can see that the integration is performed with respect to the space. Space means what? x comma y comma whatever it is. It's a surface area, right? So product of x and y, product of y and z, that will be the area. So the integration is with respect to the space, and the differentiation is with respect to the time. Therefore, space and time are independent of each other. Therefore, whether you perform in any order, it doesn't matter. Therefore, the order of operator means differential operator and integral operator, that can be interchanged. And the second, that is first point. Second point is that here we write d phi by dt because originally phi is only quantity that you have. You consider only flux, and therefore we don't consider any other independent variable. Therefore, it is written as d by dt. Now, technically, when it comes to this particular stage, whatever be the stage that you have here you have to understand carefully that magnetic field is a function of space. That means, what do you mean by function of space? It is a function of x, y, z. That is the meaning. And not only that, the magnetic field is also a function of time. So with respect to time, magnetic field can change. With respect to the space, magnetic field can change. It can change or it cannot change, whatever be the things. That means magnetic field depends on x comma y comma z. Magnetic field depends on time also. So whenever a mathematical function is depending on more than one independent variable, then the corresponding differential is a partial differential operator. So this is a very standard relation. You can't have a total derivative and keep this kind of an expression. Total derivative expression is quite different. You know how to evaluate the total differential for a multivariable function. This is not that. Therefore, this clearly indicates that the corresponding derivative should be a partial derivative, which means that it will affect only the time component only. So that is the reason why it got we have written it like that, and therefore I will write down whatever I explained. I will write down. So b is a function of space r and time t. So mathematically we can say that b is a function of r comma t. That is the reason. Okay, once this is clear, now you ask the question. Both side of the equation, both of them are surface integral, right? You are able to see that the surface is there. Therefore, you ask the question whether it is same surface or different surface. The answer is same surface. The surface under consideration is the same or identical surface on both sides of the equation. So I am talking about the integral over S. And therefore what happens is both of them are common integrals. So you can essentially cancel, no need to perform the integral because both of them are identical integrations. Therefore we will say that the curl of the electric field will be equal to minus of the dou B by dou T. And that's all about it. So that is what you are going to have here. So it is clear that this here you have this integral and this integral are identically same. So identically we are going to perform the integration. Means why to perform it? No need to perform. So if you are not going to perform any integral, then what is left out is the curl of the E will be here and the negative of the dou B by dou T will be there. So this is our conclusion, or we say that we are actually establishing the equation, and we are going to give the name once again same name, Faraday's law only. We have only rewritten according to the vector calculus. That means using the Stokes theorem. We already know something about the curl of the electric field, so I am writing down that which is equal to 0. So what is known from the electrostatics is curl of the electric field is 0. Now you can easily understand that if time dependence is not there, automatically dou B by dou T will come to 0. Therefore, you agree that the highlighted equation is a generalization to the static condition. That is the conclusion. The conclusion is the equation that we have derived just now is a generalization. Generalization means we are moving from the static condition to the dynamic case. So therefore, we have done our job successfully, and therefore we obtained one of the equations for the time dependence. So the second question naturally comes. We have written something extra, right? Namely the continuity equation. So we will go back there. And let us see how the continuity equation is going to provide additional information. So first of all, if you write down the continuity equation, it looks like divergence of J plus you have the dou rho by dou t is 0. Therefore, minus dou rho by dou t. Now, the point to be noted about this equation is, Faraday's law is an experimental evidence, or it is an experiment carried out, and we have this expression. But continuity equation, it is not an experiment that you carry out and then demonstrate this one. Okay. But at the same time, this point to be noted about the continuity equation is it represents the conservation of electric charges. Conservation of charges means you cannot create any extra charge or you cannot destroy existing charge. So what all you can do in an experiment is you only manipulate whatever is available. So in what is the manipulation going on here in the experiment is that the amount of the current density, here you have a current density, right? So the amount of the current density that is flowing in a volume. So this, whenever your divergence is coming, remember it is associated with the volume. Whenever divergence is there, it is connected with the volume. Whenever you have a normal component like this, then it is connected to the surface. So that is this is the general information that you learn from the vector calculus. So since it is talking about the divergence, it means that the current density is inside the volume of a conductor. So that means some current is flowing in a conductor, which means that the charges are flowing in the conductor. So the question that you ask is, when the charges are flowing from the conductor, where from the charges came? That is a question. So the answer is what is given by here. The charges have come from another place, or what we say that it is moving from one place to another place, right? So it is crossing a particular region. So there is a charge here, rho is there, right? The same charge which we are talking about. Where from the charge came so that it is able to flow inside the volume? That is a question. The answer is it has come from another place. As time changes, what is happening is that the charge density in the other place is getting reduced. That means at the expense of the charge density in another place, you are now enjoying the current in your place. That is the meaning. So it is like having a fixed amount of money, that if you have 1 lakh rupees, and suppose suddenly if I have 25,000 rupees in my hand, and you ask the question where from this 25,000 rupees came, means there was some fixed deposit in my account, 1 lakh rupees, and now I have the balance only 75,000 rupees there. So that means at the expense of something. That is the negative. Wow, what is the negative coming here means in my account, now 1 lakh is not there, only 75,000 is there. So it got reduced, that is the minus that you have. So whatever got reduced from my another account, that means what you call the charges in another place. What is the another place is conductor is not a single point, right? An electrical conductor is supposed to be a lengthy one. You can't have a 1 centimeter long wire and say that current is flowing there. If current is flowing means current has to flow in a long wire, or that you make the wire in the form of a circle or some closed loop. So it's clear, right, that you need to have a region of long region of space over which the charges are flowing. So if the charges are flowing in one place, it means they came from another place of the conductor. So that is the meaning of this particular negative sign there. So basically, therefore, it represents the conservation of electrical charges, and this talks about the time derivative. And that is the reason why we think that this time derivative information can be transferred to the corresponding Maxwell equation. And you already know which Maxwell equation, in which Maxwell equation we have to insert this information. We have seen some time back. And if you remember what was the equation, it is the Ampere law, right? So we are going to use the Ampere law. So before that, before going to the Ampere law, let us use the Gauss law and substitute this. Yeah, so here what I'm trying to say is we are going to use the Ampere law for this. But however, why we are bringing the Gauss law suddenly is because Gauss law contains rho here. Here also you have the rho. So therefore the question is, what is the charge density? The answer is charge density is equal to epsilon naught multiplied by divergence of electric field. and therefore this particular charge density can be substituted by epsilon naught multiplied by divergence of E. That's what I'm going to write. So that what is the advantage is that the continuity equation will be slowly getting transferred to the Maxwell equation. This is one of the Maxwell equation, right? So all the information in the continuity equation will be pushed inside the Maxwell equation. That is our job. That is why we are doing like that. Okay, so let us therefore write down like this. So now the information about the time derivative is inserted. And as usual, you know what we are doing. So the differential operator and the time derivative operator, we are interchanging. So the del operator came outside, time derivative gone inside. That's all about it. And then let us take this quantity to the left side. I will take it to the left side of the equation, so that I will be writing that the divergence of J plus, I'm taking to the left side, that's why it is plus epsilon naught into dou E by dou T equal to 0. That's clear, right? So here here divergence is there, and here also divergence is there. So two places divergence is there, so divergence is common. Divergence means del dot. So del dot is common for the both the places. So if I take it out, this J is written down here, and since it is taken to the left side, I'll put a plus, and then epsilon naught is there, and then divergence has come out here, so left out is dou E by dou T. So ultimately what happens is that you are getting a kind of new equation. Let us say that this is similar to divergence of J equal to 0. So I'll put a highlight here and say that this is the important equation that you'll have to pay attention to. So I'll put the highlight here, and the point is that what is the point is that we have used divergence of J equal to 0 in our previous lectures in the statics. In the electrostatics, you remember, whenever divergence of J is coming, we are substituting 0 there. I'll give some equation number. Okay, that's fine. So what I'm trying to say is something is known to you already. Divergence of J equal to 0 is what we are substituting, because dou rho by dou T was there, right? That is why we are substituting 0. So now what is 0 you see? Compare these two things. Divergence of J equal to 0, divergence of this quantity equal to 0. And remember, when you are adding two quantities, dimensionally they will be same. If the dimension of J is ampere per meter square, then this will also have ampere per meter square. No doubt about it. Otherwise, you can't add. Only thing is you'll have to substitute the the SI units for the epsilon naught, SI unit for the electric field, SI unit for time. Everything you substitute and simplify. You must prove that the dimension ultimately happens to be ampere per meter square. So only then you can add these two. So ultimately what happens is this: if this is current density, then that quantity is also a current density. Only thing is it is looking like E, T, etc. But ultimately, if you simplify, it will have the same dimension as ampere per meter square, and therefore epsilon naught into dou E by dou T is also a current density. So what do you understand is that in the case of the electrostatics, divergence of some current density is 0. That is clear. When you are moving to the dynamic situation, also you have you have a similar equation. Divergence of total current density is 0, but the total current density is split into two parts. One is the current density that doesn't depend on time, and there is another current density that depends on time. So ultimately the divergence is 0. So that is the knowledge that you have. So based on this particular knowledge, what we can do is that we have to replace. What is the replacement is the old J for the electrostatics will become a new J. What is new J? New J means old J plus epsilon naught into dou E by dou T. So this new J will contain the information about the time fluctuations. Okay, that means time dependent current density. You understand this? This is the quantity what is known as time dependent current density. So that is getting added to time independent current density, so that your continuity equation is always valid. Continuity equation is always valid. So now we are going to transmit, or we are going to transfer this information into the Ampere's law. Okay, that is what we are going to do now. So whatever I explained, we are going to compare the two equation. The old j should go to the new j. That is the meaning of the arrow. Basically it is statics to dynamics. That is the arrow that I am trying to draw. Fine. And therefore, so what was your Ampere's law? In the last two classes we have been discussing. So which is known to you. Let me write down. Therefore, the Ampere law has to be modified using this particular new value for the j vector. That means okay. So what is the Ampere law? First of all, remember it. The Ampere law is the curl of the magnetic field is equal to mu naught into j for the static case. Remember, this is for the static case. Now we will modify this. So if I modify how the equation looks like, say mu naught into, j becomes j plus epsilon naught into dou E by dou t. So if you do that, then now what happens is Ampere law has been updated to the dynamic case. Okay, I'll just multiply by mu naught here. Simply I'm multiplying mu naught, that's all. And that's all. And this is the important equation that you have. And you got an extra term, right? You got an extra term which is the last term. So last term is the extra term when compared to the original Ampere's law, and we will call this particular is the correction. The correction is done by Maxwell. So we say that it is a Maxwell's correction to the Ampere's law. So finally, we have now made another Maxwell equation. Okay. So sometime back, some 10 minutes back, we obtained another equation that contains the time derivative. So where was that? So already you know it, but just I want to show it here. So on 10 minutes back, we have made another equation. Yeah, this is the equation that I am talking about. So this is the equation that contains the time derivative. So final in the sense, there is nothing more to do. All the time dependencies are already taken care. That is what I mean to say by the word final here. So there are now what we have done is in the last half an hour, we have established the two differential equation. In both the differential equation, time derivative is available. One is here. This is the time derivative. And here you have the time derivative. So you see that the fluctuation of the electric field and then the time variation of the magnetic field, both of them have entered into picture. And that means we are going to discuss the time dependence of the electric field also, and also the time evolution of the magnetic field together. So this is the point to be noted, that basically we have established the necessary equations for changing to the magnetic case, time dependence, electric also time dependence. So hopefully up to this, whatever we have done, this gives you a clear information how we have made a transition from the pure statics case to account for any dynamics that are possible. So the only thing that you can further study is that, okay, these things are valid for vacuum, that is always there. And in case of the material medium, what will happen? So that is only a small change. You already know that you will have to make use of the constitutive relations, and then bring the electric displacement vector, and then the magnetic field inside material magnetic media. So if you do that, we can always rewrite the set of equations in material media. So that is only a matter of 5 minutes. We can write down that. So at this place now I would like to stop, and in the next class we will see how to write down the equation in material media. That takes only 5 minutes, and then we are ready to discuss what is known as the gauge transformation and what is meant by, say, Coulomb's gauge. So that we will see in the next class.